Hello and welcome to Everything Electrical Engineering. In today's video I'll be using the Nominal Pi model to calculate the voltage, current and power at the sending end, plus transmission line efficiency, voltage regulation for a balanced three-phase line operating in steady state. Please check out my video on short transmission lines where I go into more details on the approximation model ABCD parameters. Also, don't forget to subscribe to get future videos which will explain the difference between the different type lines, maximum power flow, line compensation, transient studies, Matlab tutorials and much more. In this example I'll be using the Nominal Pi circuit for medium line calculations. A distance in the range of 80 to 250 kilometers at 50 to 60 Hz is considered medium length. First, let's draw the Nominal Pi circuit. Uppercase Z denotes the total series impedance and is equal to the series impedance per unit length times the length. IS and IR are the sending and receiving end currents respectively. VR and VS are the receiving and sending end voltages. The shunt capacitance is halved and lumped at each end of the transmission line. The ABCD parameters are derived using Kirchhoff's voltage and current laws. And since the Pi model is a symmetrical two-port network, A equals D and is per unit, B equals Z and is in ohms, and C is Siemens. The sending end quantities are expressed in terms of the receiving end quantities here. From the matrix one can see IS is equal to C times VR plus D times IR, and VS is equal to A times VR plus Z times IR. The ABCD parameters apply to linear, passive, bilateral two-port networks with the following relationship: AD minus BC equals 1. Thus the receiving end quantities can be expressed in terms of the sending end quantities as follows. The line-to-line voltage is equal to 325 at 50 Hz and the load is consuming 200 megawatts and 150 mVar. First, let's calculate the total series impedance and total shunt admittance. The total series impedance, uppercase Z, is equal to the lowercase z times the length. Lowercase z is the series impedance per unit length, which is equal to R plus j omega L and is in ohms per meter. Uppercase Y is the total shunt admittance, which is equal to lowercase y times the length. Lowercase y is G plus j omega C, which is in Siemens per meter. Please note conductance G is generally not considered for overhead line calculations. So let's calculate Z first. 0.038 plus 0.910 to the power minus 3 times 2 pi j times 50 by the length of the line, which is 150 kilometers. This is equal to 5.7 plus j 42.411500. While the shunt admittance is equal to 0 plus 0.0114 10 to the power minus 6 times 2 pi j times 50 times the length of the line, which is 150 kilometers. This is equal to 5.372123 10 to the power minus 4, or in polar 5.372123 at an angle of 90 degrees, as this is purely capacitive. Next, let's calculate the ABCD parameters. A is equal to D, which is 1 plus y times z all over 2. This is equal to 1 plus a half times j 5.372123 10 to the power minus 4 times 5.7 plus j 42.411. This is equal to 0.9886800 plus j 1.531055.169 10 to the power minus 3. Z is equal to B, which will be calculated already to be 5.7 plus 42.411 50082J. Now that we calculated the ABCD parameters, let's calculate the phase current at the receiving end. This is equal to the 3-phase power at the receiving end over 3 times VR line to neutral. This is 250 MVA at a phase angle of minus 36.86 node complex conjugate all over 3 times 187.638 at a phase angle of 0 degrees. This is equal to 444.117574 at a phase angle of minus 36.86 amps. Next, let's calculate the sending end current IS. This is equal to C times VR plus D times IR. This is minus 4.11250.865 10 to the power minus 7 plus J.005344923764 times 187.638 at a phase angle of 0 degrees plus 0.98860.80072 plus J1.53105516 10 to the power minus 3 times 0.444117574 at a phase angle of minus 36.86 degrees. This is equal to 0.3497557817 minus J.016114385. This is in Cartesian form. In polar, it's equal to 0.386 at a phase angle of minus 24.737 kA or 386 at a phase angle of minus 24.737 amps. Now let's calculate the sending end voltage Vs. This is equal to A times VR plus Z times IR. This is 0.9886080072 plus J1.531055.169 10 to the power minus 3 times 187.638 at a phase angle of 0 degrees plus 5.7 plus J4241150082 times 0.4441176 at a phase angle of minus 36.86. This is equal to 198.7365 plus J14.45867508. This is in Cartesian form. In polar, it is 199.26169 at a phase angle of 4.1611093 kV line to neutral. The line to line is equal to 199.26169 at a phase angle of 4.141109 times square root of 3. This is equal to 344.13137 at a phase angle of 4.141109 kV. Small typo in the calculation for Vs. I wrote down 0.441176 for IR. This should be 0.444117574. Now let's calculate the sending end power factor. This is equal to the voltage at the sending end angle minus the current at the sending end angle. This is 4.16110.963 degrees minus 24.737 degrees. This is equal to an angle of 28.8981096. The power factor is the cos of the angle, which is equal to 0.087548047. Before we calculate transmission line efficiency, we need to calculate the sending end and receiving end apparent power. Let's calculate the sending end first, SS, which is 3 times Vs times the complex conjugate of Is. This is 3 times 199.26169 at an angle of 4.16110963 times 0.386 at an angle of plus 24.737 degrees. The resultant megawatt is 202.0127738 plus J 111.50083464 MVAR. The receiving end apparent power SR is equal to 250 cos minus 1 0.8, which is equal to 200 megawatts, and J150 MVAR. Transmission line efficiency is equal to the receiving end megawatt PR over the sending end megawatt PS. This is 200 over 202.0127738, which is equal to approximately 99%. Next, let's calculate the voltage regulation. This is equal to VR no load minus VR full load all over VR full load. VR no load is equal to Vs over A. These are voltage and magnitudes and line values. This is 344.1313 over A, which is 0.986080072 plus J 1.531055 10 to the power minus 3 minus 325 all over 325 times 100. This is equal to 7.41784%. I use Matlab here to confirm the calculated result for Z, Y, the ABCD parameters, the sending end current and voltage, power factor, voltage regulation and transmission line efficiency. Ignore any small difference, this is due to rounding. I'll be doing Matlab tutorials in further videos, so please don't forget to subscribe. Thank you for watching. Please don't forget to check out some of the other videos. If you felt like you got any value from this, please like, comment and share.